Okay, everybody, the first talk will start now. Thank you for your patience again. And with much ado, Dániel.
Thanks. So, hello everyone, I'm Dániel Vigovszky and I work at Prezi in a team called Coedit. And in this talk I'm going to give a short introduction first of what our team is doing, and after that I would like to show you what kind of Haskell projects we have, and then talk about two more specific topics, our build system, which I think is quite unique and powerful, and then I will demonstrate what kind of testing we are doing. You will understand better if I started the introduction. So, yeah, we launched our new product about a month ago, which is important because this is the first product that uses Haskell code in production. Our previous product didn't have any Haskell relations. And what is a Prezi from our team's perspective? Prezi, it's a document. It consists of a hierarchy of document elements, and you can imagine it, or you can call it a PDOM, a Prezi document object model, and it looks something like this. So when I'm talking about PDOM, you have to imagine that we have a Prezi. It consists of objects, background properties, styles, and such similar things. And the important thing is that this PDOM evolves continuously as we add new features. We add new document element types, we add new properties, we are doing experiments like creating small branches of our product and trying out new things. And to demonstrate it, we had about 75 commits in the last year, only in the file that describes this document object model. And the other challenge we have is that we are supporting multiple platforms. Our main Prezi editor is a web-based editor. It's implemented in Hex and TypeScript. We have viewers for mobile platforms written in C++. And we have our server side for editing Prezis written in Haskell and Scala. And what do we expect from this document object model is we are serializing it to XML. It must support undo, redo, and of course edit simple updates and stuff. There are some invariant checking, like you cannot create an invalid document when you are using our document object model API. And a very important thing is co-editing, when you are creating an editing session on the server side and joining with multiple users and changing the document together. And yeah, that was the introduction. So let's see how Haskell comes to the picture. This is kind of a dependency graph of our Haskell projects, and it's just an overview. I will start from the top, the PDOM schema, and it consists of two DSLs actually. The first one describes the object model itself, what kind of elements we have, what properties they have, and this is a fragment of it. It's a Haskell DSL. You describe basically the data types of this of a Prezi itself, of the document. And there is another DSL in this project which describes the co-edit protocol, because the clients are communicating with our Haskell service through a sock.js streamed protocol, sending JSON messages, and this is also specified in a DSL, which looks somehow like this. So if you take a look, this describes a single message that the server sends back to the client when the client tries to reconnect. So this is the response from the server. And what are we doing with these DSLs? The next project we have is the code generation. As you can see, we have the schema that I just explained. and it goes to the next Haskell project called bidon codegun, where we are building different models from the schema's AST for the different backends we are supporting. And after that, we are using, in most of the time, we are using a Haskell library called Ada, which is a text templating library, very similar to the Liquid library, which is more well known probably. And we have some custom generator codes. So these green ones are the source artifacts that we are generating with text templating. We are generating Hex API for the web, C++ for the mobile viewers, Haskell code for our service, and Scala code for our other service. And Spaghetti is kind of a JavaScript glue code for interface definition language that we are using. It's not important now. And we are also generating JSON from the schema DSL for non-Haskell code generators. So it's basically a form of the AST of the DSL of the schema. It's used by some TypeScript codes that are generating even more code from it. We are generating an XML schema for file format. We are generating XPath expressions for some other purpose. One of the services have to find the exact location in our document of media set URLs or something like that. And we are also generating QuadIT protocol documentation, HTMLs from the protocol DSL. And once we have these generated codes, the next important project or module is the bidon QuadIT and Haskell, which implements operational transformational algorithms. I don't really want to talk about it because it's not my area, but the main idea is that you are in state X, and one of your clients goes to state Y, the other is to state Z, and the server has to figure out how can both clients go to common state again. And this looks like one of the clients sends patch A that modifies the document, the other sends patch B, and then on the server side we can calculate the B patch merged with A patch and the A patch merged with B patch and broadcast them to the clients, and then they can be synchronized again. And these merging and patching algorithms has a lot of laws that they have to conform to. This is not really important from this talk's perspective, but I wanted to mention it. And yes, so patches are the data structures that describe how a document changes, and this is also generated from our DSL, except some generic cases like arrays and maybe types, which looks like this. This is the patch data structure for modifying array of any type. You can either replace the whole array, insert a new element, remove a new element, or modify an element. But this is the kind of patch data structure that is generated from the DSL. Like the Z object is the basic object type of a Prezi, text, an image, everything that you see here is a Z object, and this is the top part of the patch data structure that we generate for it. And yeah, for each patch, what you have to implement is patch application, patch inversion, patch merging. Basically, you have to implement this type class, which is not completely generated, but written by hand. And once we have this QuadIT library for Prezi documents, we also have a QuadIT server, which I don't really want to talk about right now, but it's a stateful server. It communicates through SockJS, as I already told you. It's our own library based on Warp for SockJS, and we implemented some actor-based concurrency, which is similar to Akka a bit. And actually, why I mentioned it is that these two libraries will be open source soon. So you can take a look in a few months, I think. Yeah. But otherwise, I don't really want to talk about the server in this talk because it's a completely big topic in its own. And finally, we have a lot of testing code. We test whether these merge rows that I mentioned, merge termination applies for the patches that we implement. We can test serialization. We can test the wall co-edit sessions. But I will talk about it in the last section of this talk. Yeah. Okay, so the two more specific topics that I want to talk about. First one is the build system. And as you probably saw, we have a lot of projects that are depending on each other. And they are, of course, also depending on a lot of package, third-party libraries. And we also have a lot of other projects implemented in other languages that are depending on the code that we are generating. So let's see how is the problem, or what problem we had to solve. Yeah, so we have a lot of Haskell projects that are depending on more than 100 third-party libraries, actually. And compiling all this takes a lot of time, like more than an hour, I don't know exactly, because we are not doing it anymore. And yeah, compiling it from scratch. Why will we compile it from scratch? Because we may work on multiple branches, we have new developers all the time, and we are using Jenkins. But yeah, so the first use case when you want to create a new branch, it was a problem when we were using Cabell sandboxes. Now it's not a problem anymore because Stack solved it with the global package cache it has. Okay. New developers. Why do we have new developers all the time? Because we have that schema that I showed you, and not only the Haskell developers, but all the client developers of the company want to modify the schema time by time when they are adding new document elements or properties to the system. And they don't care about Haskell at all. They don't have GAC. They don't have their environment set up. They just don't want to worry about it. And on Jenkins, we are having auto-scaling nodes. So caching the third-party stackage packages, for example, is not really possible because of some reasons. We have parallel flow jobs which are copying build results from one node to the other. So it's again a problem that most of the time you have to build from scratch unless you have a good build system that we had to solve somehow. And here's the idea. So let's treat the GAC package databases as binary artifacts, as a single unit of binary artifacts. And then on top of the Haskell level dependency handling, when you are depending on Haskell libraries, all projects can depend on these package databases. And if you have that, you can have chain package resolution. I will show a diagram about it on the next slide. And with this chain package resolution, we can have a common empty base project that integrates all the third-party dependencies that are commonly used by all our projects. And it will sit on the beginning of this chain. And let's implement also transparent compiler and tool installation, like the JavaScript developer who doesn't care about Haskell really don't have to care about Haskell. It's just installed for him and compiles the schema. And let's use our CI with Jenkins to build binaries for every platform. So if someone don't want to compile the whole Haskell ecosystem of Prezi, they just download the pre-built binaries. Yeah, and one more constraint that we wanted to be able to select a subset of our projects that we want to build locally and get the other dependencies that we are not working on right now from the CI build binaries. Yeah, and actually we implemented all this. It's a Gradle-based implementation, but don't worry about it. The idea is completely reusable. So if you never want to touch Gradle, I can understand it, but you don't have to. You can still reuse the core idea. And yeah, so we started with using Cobble's sandboxes, but now it's deprecated and we are only using Stack. And we are using Stack with two important Stack features, the extra package databases and extra dependencies. I will explain how in a minute. Yeah, so this is the diagram that I mentioned. Let's take a look. So the boxes on the top are package databases, and I've copy-pasted the three. So let's imagine it's dependency 1, 2, and 3, and not dependency 1, 3 times. Yeah, so on the left, top left, we have the global package database that only contains the core, the base package, and some others, and what comes with the compiler. After that, we have these downloaded binary artifacts containing the package databases of our Haskell projects, dependency 1, 2, and 3 in a order. In a dependency order. And on the top right, we have our own project that we want to build right now. It's a Stackwork directory, which is also a GAC package database. And we start the whole thing from the Cabal file. And we don't write Stack files by hand, we are generating them. And we are using two tools here. One is the snapshot versions tool, which I will explain later, and the other one is required for the unpacked package databases to fix the paths in them. So let's see how building a project looks like. What build steps do we have? So first we are downloading the dependent projects package databases. They are simply zip files uploaded to Artifactory with Gradle's publishing mechanism, but it doesn't really matter. You download these package databases somehow and extract them. Then you have to run the sandbox fixer. It was implemented by my ex-colleague András Schlemmer. And what it does is that the package databases contain some I don't remember exactly. I think it contains some absolute paths and some hashes of the dependent packages. Anyway, this is a command line tool that fixes these things in the extracted sandboxes. So what we achieve with it is that you don't have to extract the sandbox, the package database, to exactly the same location as it was archived from. And also, this is the main feature, I think. And then there is another tool called snapshot versions. To explain that, let's go back to this drawing a bit. So one important thing is that we cannot use the Stackage LTS packages, because how Stack works is that if you specify that you are depending on, LTS 3.22, then it will download all these packages to a global package database, and it puts it here in the chain, just before your Stackwork directory. And this means that all your dependencies will not see it, because how the package database chaining works. So what we had to do is that we always use just the compiler itself, and we add all the dependencies as extra dependencies in the Stack burning, which means that Stack will put every dependency to your local package database, except if it finds it anywhere in the previous package databases that are chained. And this is why we have a common base package database, which is put to the front of this chain, which contains all the dependencies that are commonly used by all our projects. So what this snapshot versions tool is doing is that it helps generating the stack YAML file by providing, because I wanted to keep the feature of stackage that it has a well-defined set of package versions that are working together, and I didn't want to lose it. So snapshot versions fetches this package version database from stackage and also reads your cabal file to find out your dependencies, and generates the stack file by adding all these dependencies as implicitly pinned down versions of these dependent packages. And as you can see on the top, this is the package database chain for the code itself project. And this is why you don't want to write this by hand, because it's a very huge stack YAML file. So next step, what the best thing about this build system, in my opinion, is that after this fourth step, you can just use stack. You don't have to care about the whole Gradle, wrapper, whatever environment, because this stack YAML file is working on its own completely well. So at this point, you can just use stack or whatever tool that knows about stack. And finally, you can package your local stack work directory and publish it to Artifactory or wherever you store your binary artifacts. So this is the main process, and what results we had with it. We are using this for more than 1.5 years now with success. We really like it, and also open source most parts of it. So yeah, first step was adding this small package chaining to stack, which I had to do. After that, we wrote a Gradle plugin. As I said, it doesn't have to be a Gradle plugin. It's basically just calling all the other tools and downloading and uploading dependencies. And this is András's Sandfix project. This is my snapshot versions project, but all of these are available, so this is quite reproducible. I mean, this build stack. And one more site-related project that Prezi has is this one that's called Pride. It's for the local development. I mean, you can add a set of projects that you want to work on, and then they will use each other's build output. But otherwise, every other dependency will use the binaries from the Artifactory. Yeah, this is the feature that it implements. And we are building all our Haskell projects on Jenkins for all our platforms, which is Linux and OS X. And we even managed to wrap everything, like installing GAC and downloading everything. So non-Haskell developers don't have to care about it anymore. They just say Gradle build after they modify the DSL, and they have to wait a bit, but after that they get their fresh generated API. Yeah, and the final topic is testing that I wanted to talk about. So, as you probably saw now, PDOM is a core component. I mean, it has to work. It needs a lot of testing, and it must work exactly the same on all our platforms. Otherwise, very strange things could happen. And I will talk about 4 different levels of testing that we are doing. One is serialization testing, how we test our co-editing libraries, how we test our SockJS protocol, and the most interesting part is how we do integration testing. So let's start with the serialization. Yeah, so of course we can generate arbitrary Prezi documents with QuickCheck. And then what we are doing is that we save these generated XMLs. So within a QuickCheck property, we can save this XML to the disk and then run one of these tester tools for all our target platforms. There is one implemented in Hex, there is one implemented in Haskell, there is one in C++, and there is one in Scala, which do something like reading this generated random Prezi XML, maybe doing something like modifying it and undoing the modification or something that we want to test. But at the end, it has to. We are assuming that it's in the same state as it was when it loaded the Prezi, and then it writes back to disk with its own serializer, and then the QuickCheck property can read it back and compare the result document with the original one. And with this, we can have QuickCheck-driven serialization tests for all our platforms, and it proved to be very useful. And it found a lot of issues that you would never think about. And the best thing about this little framework is that it's generalizable and can be used for testing a lot of other stuff among the platforms. Like, if we add the ability to generate arbitrary patches for a given document, here it's important that we cannot just generate a random patch. We have to generate a patch that is applicable for a given document. So we have a typeless for just doing that. As you can see, these document type, and it generates a patch that is applicable for that document, and it may even fail. Yeah, so once we have this, we can do a lot of things. For example, we can test the merge logs that I mentioned for a second in the first part of the talk. When you write a new data type, a new patch, and you write the patch merge function and the patch inversion function, you can be immediately sure that you are applying to the merge logs because it's tested. Yeah, here's an example which tests this very basic load that the inversion of the inversion gives back the original patch. It looks something like this. We are generating a document and called X. We are generating a patch called A. We apply the patch and then calculate the inverse twice and just compare the two. And we apply the result of the inversion and then compare the two patched state of the document. And we have tons of tests like this. And what I mentioned in the previous slide is that we can also test other platforms' patch algorithms using the fact that patches are also serializable because of how the JSON protocol works. So exactly the same way as in the serialization case, we can generate a document, generate a patch, save them to disk, and then from the QuickCheck test itself, we can run the Hex implementation that loads them, applies the patch, writes down the result document, and this way we can integrate all our platforms in one test framework, which is pretty cool, I think. Yeah, the protocol is very similar. So yeah, it's almost the same as the XML serialization test, except that we are writing out JSON protocol messages. So let's talk about the integration test framework that we have. It's not really readable, but how it looks like is that we Dockerized all our dependencies, and we are even running the code server itself in a Docker container to be as close to the production environment as possible, because we experienced some strange behavior between how it runs on Mac and how it runs on Linux. Anyway, this blue stuff is a Firefox, which runs JavaScript code that uses our JavaScript API, which is generated from the schema. it is the same API that the real Prezi editor uses to connect to the coded server. And the Firefox is driven by Selenium, which is driven by the Haskell package called WebDriver, I think. Yeah, and we have a test DSL, which is very powerful. I will show an example soon. And on top of this test DSL, we have all kinds of tests, like we have simple API tests, which are not really using the fact that we have the whole infrastructure running in Docker, but we have real integration tests where we can, verify that once you made a change through the coded server, it was saved somewhere in the infrastructure. We have interleave tests and correction tests, which I will talk about a bit later. So let's see what this integration test DSL is, because that's my favorite part in it. So here's a small code fragment. As you can see, probably you can switch between browser windows. Here you can launch multiple browser tabs, simulating that you are connecting to coded from multiple Prezi editors. Switch between them. You can observe network events, wait for them, and you can also execute arbitrary JavaScript code with the help of JMacro. Yeah. And you can also write client-side assertions that are converted so that are read from the browser, and these are also implemented in JavaScript code that is embedded in the Haskell DSL. And what is not visible on this example is that you can also manage the whole test infrastructure, like you can start or stop services, you can check whether code saved something in the database, you can access the data storage where it stores the Prezis. You can simulate network errors, like breaking the connection between one of the browser tabs and the coded server, and see how reconnect works, and all this stuff is manageable through this test DSL. And yes, and the final thing I wanted to talk about is that we are able to generate even arbitrary coded sessions, which you can imagine, like with QuickCheck and JMacro and the code generator, we can create sessions for multiple JavaScript editors by generating JavaScript code that are executed parallelly or in a given order, and we can verify how the patch merging and how the conflict resolution works in an arbitrary random scenario. Yeah, so we are basically generating arbitrary JavaScript code here, but it's not completely random. It's simulated on the generator side. So the code that generates these JavaScript codes knows in advance what the expected result is, and we are parallelly running the real coded code and this simulation and check the results. Yes, so I was a bit fast, I think, because it was only 35 minutes, but basically that's what I plan to share with you, and I'm ready to answer questions if you have. Thanks.
One question.
Yeah.
You mentioned you open source some libraries. Those libraries are on package, or I can just find those libraries in your GitHub?
Can you repeat the question?
Yes. So the question is whether our open source libraries are on package or where you can find them.
Yes.
We didn't open source the two libraries that I mentioned yet, but it's planned. So, but once it's open sourced, I'm sure that we will upload to package. The other links that I showed were basically tools which could be uploaded to package, but they are not right now. So there are two Haskell projects that is open source, the sandbox fixer and the snapshot version generator. These are just on GitHub right now. Yeah.
Okay, thank you.
Yeah.
I want to ask, I know you said it was not your area of expertise, but the merging of the different patches
Yeah.
In co-edit mode, how did you know which rules the code has to satisfy in order to merge it correctly? How did there were like, I don't know, 10 or 15 rules?
Yeah.
How did you discover those rules, or
Well,
how did you know?
here's is the original author, I think,
Uh-huh.
which is Peter and Csaba, I guess. Peter. So, would you mind explaining OT?
Can you repeat the question?
Yes, how did you know which rules the code has to satisfy in order for the patches to be merged correctly when multiple users are editing the presentation? How did you know which rules you have to apply or which invariants it has to satisfy?
So we developed the general theory of patches. Is so there is a lot of room for different decisions, and so this general theory has some rules to satisfy, but there is a lot of room for different
Interpretation?
yeah, not so. For example, if you would like to resolve difference in changes, then you can do it several ways, such that if you obey the rules, the general rules, it will be good.
Yeah, but there are also user experience related considerations in this. So maybe you can implement the merging in different ways, but some of these implementations would create a user experience that is very unnatural for the users, and yeah, this is a continuous process when we are refining these merge algorithms.
One more question.
Yeah.
For the generation of JavaScript. So basically, the JavaScript you generate in the J macro, it's triggering the changes in the UI, in the editor, in the presentation, or?
We are not really, so we are not including the editor itself in these integration tests. It's one level lower. So we are only testing our coedit API, which is also used by the editor. So there is one more level of test which is not really related to Haskell projects, so I didn't include, where the whole editor is tested as and integration tested with coedit, but it's not Haskell driven. It's some kind of JavaScript test that I don't know much about.
So the JavaScript you generate, it triggers another JavaScript API?
Yeah, it triggers so for example, we generate the error patches, generate an arbitrary patch, and with the code generator that generates everything that I mentioned, we also generate functions that can convert patches to JavaScript code, client code. And using this, we can generate a set of patches. From that, we can generate a set of JavaScript comments. And basically, that's how this test generation works. Yes?
Regarding the integration DSL, like how did you arrive at that particular form of the DSL? So who provided feedback for it? How did you sort of iterate?
Well, it's only used by our team, so we just wrote it for ourselves, and we continuously refactored it even it was not satisfying, so nothing special trick or anything. Okay, if there are no more questions, then thank you for your attention.
Okay.